All
All
right.
right. Hello, everybody. I'm Zack Zukowski, and I am a team member at Harmoni, which is a research lab that focuses on audio and music, and we're under the Stability AI group. So a bit how about how I got started with that. As Era was mentioning, I was first part of this group called Dadabots, and we made infinite live streams using sample RNN. And our first models were kind of adapted from speech models that were intended for, kind of just babbling speech, unconditional autoregressive models. And we extended the receptive field for those and modified the architecture that let us do very long context windows that just kind of went on and on and on with no song structure. The first thing that we did with that was infinite death metal live stream. This was picked up by Vice, and we got a whole bunch of people, like 1 million viewers in this live stream. And it's been running ever since, like 2019. So it's still there today if you go to YouTube. We still have this thing going for years. That's how we got started. Then later, this Harmoni Research Lab started. And this is when diffusion was starting to take over, and the world of diffusion and transformers were where things were going. Being at Stability, the big focus was, stable diffusion had already had a lot of success. So we were looking at how do we apply this to audio. And that's where I joined. We were thinking about how to really get good song structure in music, because that's what RNNs were lacking. We needed to have parts that could return. It was coherent over like 5 minutes of music. That was what we were seeking. And diffusion is a really good way to do this compared to a language model. Things like Jukebox were already out that could prompt lyrics and allow to have kind of the background music be there with a suggestion of what the lyrics prompt might be. And this is, next token prediction. What is even cooler about in the music space, especially in the latent music space, is that now we're not autoregressive over time, but you can think of diffusion as autoregressive over frequency. And Sander Dielman originally made this point in his blog. He's a researcher at Google for audio. And so you start with noise over the entire context, which could be like three minutes. And you're denoising this. So the structure is already there. So really you start with low frequency things, and eventually you get to higher and higher frequency details, the higher frequency noise, which is what the denoising process does. And that's why it works really well for music where you want to have good song structure. And that's primarily what we focus on. So when I joined, there was already a tool that was web-based called Stable Audio 2. This was trained on a licensed data set of music from Audio Sparks, who is a production music company. They try to get their music license out to film, games, and they have a bunch of composers, and they pay a royalty to those people. So this is a 50-50 royalty split model we had for this. But the issue here, along with many other models like Suno Audio, is they are on an API. You can't locally put them on your computer and fine tune them on your own music or on a group of regional music from a country that maybe wasn't represented in that data set. And this limits the way that you could actually control your own tool set as a creative person. I studied technology, and I'm coming from being a musician, pushing towards synthesis with music technology, realizing that machine learning is going to be the thing that is going to allow us to get beyond sampling and get beyond working with symbolic data like MIDI, which is more like a sheet music format for computers that tells you where the notes are in time. But what I really loved was punk, jazz, death metal, psychedelic music, and things that, the timbre, the tone, the characteristic, the style, the production is really what gives that music its special cultural impact, not just the notes, not just the theory or the harmony. So this was really the guide that led us to what I'm going to talk about primarily in this, which is stable audio open. So initially we have, if you train on music data, you're going to be able to do longer songs. So here is our music model that was out initially, just so you can understand a little bit of what that's like. Oh, actually, I'm not logged in, so we'll skip the sounds, but yeah, I'll get to the stable audio open is primarily a sound effects model. It only works on 47 seconds, and that's because what our goal here was to make something that could run on consumer hardware like a RTX 3090 or 4090, because we see that, yes, you can democratize and bring up the quality of creativity for people who maybe don't think about writing songs, or maybe are working in ad agencies where they need background music, or they're just a content creator that wants background music for their video. But I want to see professional tools make the professional reach a new level of art and weirdness and cool creativity that they hadn't been able to do because they're spending their time on a lot of other, maybe not the most creative, maybe not the most fun tasks. Having this in mind means that we need to have the weights downloadable for people. We need to let people take the model and fine tune it on all of their own favorite songs and put the prompting in the way they want. And furthermore, it shouldn't just be text to prompt, or prompt to input with text to audio. It should be something where audio could be prompting the audio. And I can say, listen to the vocalist here, listen to the drums in another track. Can you merge these ideas and then, create a composition using this structure and then push the surface into somewhere that the text is steering? And these are the kinds of workflows that we hoped with stable audio open. We wanted to have something transparent where everyone could feel good about where the data was coming from and that they could download it, run it locally. And so the motivation for this was that, most of these models, such as Suno or ones that are behind an API, have no accessible weights. It's unclear how the training data came about. And if you're a music company where, your customers are artists, as mentioned earlier, this is a point of discussion, how we're going to get people who are creators paid or bought into using these tools, and how does it actually make their art better and not replace them in some way that isn't really helping their work. So we have a paper coming out. I'm going to ICAST in India next month to present our work here, Stable Audio Open. So when I joined, I really focused on how we can make sure that all of the data that comes from websites like Free Music Archive or freesound.org, with the user giving a license of Creative Commons or public domain, how do we verify that some Justin Bieber or some kind of pop music didn't sneak its way in there because users are uploading this stuff? And we went through this whole rigor of figuring out how to do this in a way that is safe for the company and safe for the community of people who had put this stuff up online originally. Yeah, so in the end, we ended up with a stereo model that can do high quality 441K audio. It generates 47 seconds. So you can not make full songs here, but you can generate loops, sound effects, backing tracks for films, something that you can sample later yourself in your own creative workflow as a music producer. Just maybe you're a vocalist and you have a guitar part and you just want a drum beat at 120 BPM in the style of funk. These are ways to create ideas and start sketching quickly now. Yeah, so ways that this could be applied. There are quite a few ways. Game design is obvious because games are already generative, and having a very fast model that can run on a consumer device like a cell phone, potentially, even without any GPUs, allows for all kinds of things to happen interactively, guided by the user. Film production, obviously there's this approach where you could look at conditioning the optical flow from visuals and find some kind of rate of motion, or like RMS, that could be mapped then to activity of certain sounds. So, when there's a video of somebody dropping a ball, the optical flow could be mapped onto the bouncing ball sound automatically, and we can get automatic Foley by adding on control net style control to the unconditioned part of the model. Music production, obviously, that's why the team formed. We're all music producers. We wanted to push DJing to a point where it could be live prompted songs you've never heard. We wanted to push all of these live expression for music in a new direction, hear new sounds, hear new genres, hear new cultural combinations we haven't heard yet. And a model is actually really great when it's able to extrapolate from different categories of sound and create something hybrid, which is sort of how we think of it internally. It's like this spaceship that allows us to reach all the spaces in between the data points of the constellations that we already had put into the model and figure out what are the styles in between there. And then it opens up all kinds of interactivity now. Not only if I'm a musician giving a live performance, I could prompt the audience, we could co-create together on stage. All these types of things could happen on the web, on live streams. A group of people could steer an interactive live stream together. And cool social interactions emerge out of this. So the technical architecture, what actually is Stable Audio Open? It's made of basically three components. There is an autoencoder, which makes it different than some diffusion that works directly on the raw data. The first model we put out was called Dance Diffusion by Zack Evans, the founder of Harmony. And that just worked on the audio itself. And the downside here was that because the audio data, 44.1 samples per second, that's so many predictions to make compared to words or tokens in that way, that you can't train it or do inference on a very long time window. So the autoencoder is so important because that allows us to compress the audio into latents that then allow us to work in up to 5 minutes of input and then decode it later after the diffusion process happens. That gives us really long context windows, and it also allows us to create more fusions of what is in the text prompt. The diffusion part over here, this is just standard diffusion, and what we do is we cross the latents from the auto-encoded audio with T5-based text conditioning as a language controller, and it learns to diffuse that is conditioned on those signals. One thing that I think we put so much time into was our autoencoder, and it's an overlooked space, I think, in images because they don't have the same issue. But I think as we move to video, things like autoencoding and compressing data that way will be very important. So the data transparency is actually a big crux of this paper. We took almost 500,000 recordings, over 7,000 hours from Free Sound and Free Music Archive. And we made sure all this was properly licensed under Creative Commons, as I mentioned. And we did this by detecting which parts were music. And then we used a third-party tool called Audible Magic, which does fingerprinting. It looks at our piece of audio we gave it in query, and it says, is there anything, any of the major labels, Sony Records, Universal Records, etc., that matches this down to like a 20-second fragment? And if so, we manually went through and we removed a bunch of data that most of the examples were, I'm sitting here making a video about driving in a truck and music's on in the radio. and that music got leaked in. So we were very careful to make sure that none of that stuff was in there. And we did a memorization analysis because, when you get smaller data sets, smaller models, you want to really make sure that it's not just overfitting memorizing. And the closest that we got were, if you have a sine tone at 1,000 hertz, there's only one way that can really come out. Or a storm is going to generically pretty much sound similar. But we have examples where, if you prompts for a clarinet playing a scale with, from very specific tags, like the kind of microphone, the rhythms will be different, but the scale might be the same. So in general, we find this the right amount of variation to have some creative kind of balance in the rhythms. And yeah, the main workflow here is that, as a content creator, you have a lot of different ways you might want to interact. Like being able to control it from the audio, like beatboxing, is one of the main things I work on. I work on controllability from the music perspective. So like without explicitly teaching it about music theory, can you extract musical features like chroma, which tells you about the main pitches that are present, or the harmonies, if you build those up. Or if you take BPM or rhythm detectors to know the downbeat and other downbeats, can you create a skeletal structure that then gets filled in with the details as the diffusion process happens? Having just lots of control of if you're controlling the rhythm, the melody, all these different things, really gives it a lot more power. The other really amazing thing about it is we have this community now of open source people who are building off of what we've done, and that's what it's all about. So, for example, when we put this out, a person in our community, Lyra, made a 4-hour video about how to fine tune it and taught the community that this was, done with some rented GPUs. But we've had people in the community share that they've, made the model a little bit shorter receptive field. So they've gone down to like 10 seconds to just do sound effects, and they can do it on like a consumer GPU on like a gaming PC. Since then, we have been working with diffusion, which has like distillation. So we're also doing this distribution matching distillation, as was mentioned in the previous talk. And we just got a stable audio model to be distilled into one that is 30 times faster and runs on an ARM CPU on a mobile phone. So this was a partnership with ARM that just happened a couple weeks ago. And what's really cool here is that, yeah, you can generate text to audio, large model, corpus music on a mobile device. That's going to change so much, not having to be on the internet. I can be in the forest creating ideas, sketching my song away from everybody in my Zen artist space. I don't need to be subscribed to an API in this scenario. And this could be built into other applications, games, and all types of other things. So yeah, I think that's really exciting. And to quote Frame, our current CEO, he says, we want to be where builders build and creators create. So that's why open source becomes important. Open weights become important, that we can deliver the weights. We can trust that's transparent, that we're happy with that. People can build and make really fast things because, making real-time music on stage interactively is like where it all needs to go. The final thing we did recently was we made a quick documentary. You can check this out about our creative workflow. Some of us in the community and some of us who work at the company did this thing called prompt jockeys. So yeah, it's like DJing, but harder, because with DJing, you're usually playing other people's tracks. But with this, the tracks don't even exist yet. You're prompting them live with a neural net. And it's actually extremely hard. I've been doing them. I went to South by Southwest and played like 3 prompt jockey sets recently. And it's just like you're on the edge of your seat, just trying to like keep up with how do I mix in this track that I really don't even know where the drop is. But everybody knows that, and it becomes this improv game. It's been really fun. So yeah, check out prompt jockeys if you're curious to learn more about our creative workflow around this. Yeah, so the model really excels at environmental sounds and field recordings. Yeah, we basically have it ready to go at a less of a consumer level, but more of a business-to-business approach, or just directly to music hackers, directly to artists. Basically, you're allowed to use any of this stuff if you're not a $1 million+ revenue company. So we sort of have these two lanes where there's a more corporate use of our models, and then there's just the community use, which has been really nice. And some extensions, yeah, there's the Presto paper that I would suggest checking out. This is where one of our interns, Zach distilled a model for control. So without any further, without training in the base model, you can just distill and get a control net style thing. Yeah, recently I've been getting into live coding. I don't know if anyone knows what live coding is, where you make beats like right there on the spot. This is what live encoding looks like. It's code that you can see the MIDI going by, and hooking that up to something like Gradio, OSC. Gradio is a way to demo models in a simple UI. So the community has built a way to connect live coding environments like Strudel and Title Cycles to this. Also, there's a paper that uses optical flow of videos and learns how to map that to sound events, as I was kind of mentioning before. So yeah, a lot of really cool things coming out. And I encourage you to try it out. Our model's on Hugging Face, papers on archive. We have a Discord community for Harmoni where you can come talk to us and we'll help you get going. And yeah, please reach out for collaboration opportunities, especially anyone making cool media or games. Would love to see what you're doing.
Awesome. Thank you, sir. We have time for one question.
Yes. Yeah, good question. The ARM model, there are two things that happened. We distilled it into a smaller model. So we're going to be releasing a paper for that and code for that soon inside our stable audio tools repo. But they also did some matrix multiplication type wizardry that is a little over my head. It works down at their level, at the hardware level. So they further optimized some of those things. But yeah, that got 11 seconds of audio generating at 8 seconds. So it's fast in real time, but once the distillation tool has been released, you could get it to run in CPU at that point. But they did a little bit of extra optimization for harmonies. Awesome. Well, thank you so much. It's an honor to be here.
Thank you, Zack. Frankly, in the multimodality space, there's not enough open source